Here we have the another problem of the binary search tree, which is the recover binary search tree. Here what the statement of this problem is, or what this problem says is, we have in our binary search tree we have given some wrong nodes. We have to swap the incorrect pair of nodes. We have to first find the pair of the incorrect nodes, and then after finding those nodes we have to interchange means we have to replace. Interchange means we have to swap both the nodes. And here are in the description, here are the examples on which we can dry run our problem. And there is some constraint: number of nodes in tree, ranges, and node values, and follow-up. Means a solution using this much space is pretty straightforward. Could you devise a constant space solution? We have written the solution, which is having the time complexity of big of n because of in order traversal, because we are traversing all the n nodes of our tree, and having the space complexity here is big of n. Why big of n? Is because in this function this is base case and this is our recursive call of this function used. That's why it's recursive call stack, recursive call stack of n depth. We have the space complexity big of n. Space complexity here comes because of the call stack depth or recursive call, and this swap logic uses the variable. That's why its space complexity is constant. We cannot count its space complexity. Only this is the main function from our problem, and this is the function which we have passed. Inside it we have passed the root and made it above. We have passed the tree node star root. In the in order we have passed our root, and this is our recursive solution. That's why our space complexity is big of n. And we have initialized the three variables: first, previous, first, and second, all of them by null. This is base case. If our root is null, root means current node at which we are standing, and we are calling the in order for our roots left. And this is condition check. Previous, if our previous is non-null and previous value greater than root's value, this is the condition to check whether we will. This condition is to find the wrong pairs that will be arranged in our tree. Then after fetching those pairs, we will swap that pairs to get the correct order. Also, if this first is null, then we will store the previous in our first and root value, and after if condition we will store the root in our second, and for update the previous for next iteration. Previous is equal to root means we are storing the root in the previous. We have updated the previous for every next iteration, and we will call here the in order for roots right. Simply this is for in order we are following left and root, then right. So this is left part and this is for root part and this is for right part. This in order function is to do in order traversal, and this recovered by BST is the function to. In this function we are writing the swapping logic. We have only passed the function in this main function. We have passed this ENOT function in this main function recover tree, inside which we passed the root that were passed on our ENOT function before that we made, and then we wrote a logic to swap the values. This is the simpler method that we have already studied earlier in our arrays topic, temp swap method, swapping two numbers. Well, in this step, that first of all we have to perform the in order traversal, then till here, this point at the end of this in order traversal function. After traversal, we will get the first and second value, I guess. Then after this function call, we will reverse the first and second value by this temp swap logic. That's it.